This is multivariable calculus, and in this video I'm going to talk about section 15.3, double integrals over general regions. And before I really get into the setup on these integrals, I just want to talk about the mechanics of actually solving these out. So when we looked at double integrals in 15.1 and 15.2, we used approximation methods, and then we talked about double integrals over rectangular regions. And when we did rectangular regions, we were just substituting constants into our antiderivatives every time. So it was a fairly straightforward process. Now that we're going to start getting into having limits of integration that involve variables, it'll be a little bit more complicated, and the setup will definitely be a lot more complex than what we were doing before. So here's a really simple example, just so you can get a feel for how this is going to work. So we have a double integral from 0 to 1 and negative x to x squared, and our function is y squared x. We're going to integrate with respect to y and then with respect to x. So when we solve this thing out, the process is basically the same. Like I said, it's just going to be a little bit messier because we've got to do some work with the antiderivative here and a little bit of algebra to get it simplified down as opposed to just constant values. So my antiderivative here with respect to y would be xy cubed over 3. And I'm going to evaluate that from y is equal to negative x to y is equal to x squared. And again, you don't have to write the y equal to there if you don't want to, but a lot of times it's good to have it there just as a reminder of what you're trying to do. Okay, so now that I've got that all set up, I'm going to go through and plug everything in here. I've got my integral from 0 to 1, and when I plug in, I'm going to get x to the 7th power over 3 plus x to the 5th Okay, now that I've got that all set up, I'm going to go ahead and plug in my limits of integration. So that's going to give me the integral from 0 to 1, and I'm going to get x to the 7th over 3 plus x to the 4th over 3. And it's a plus because I had a minus a negative there, and that'll all be dx. And now from here, we're just solving a single variable integral, right? So at this point, I'm not going to show you the rest of these steps because you know what to do. You would end up with 13 over 120. Okay, so not that difficult to do. I also gave you a really simple example there. Sometimes you're going to end up using more complicated integration techniques on both your inner or inside integral and your outer or outside integral. So, you know, these can get a lot more complicated, but the same general idea always applies. You work from the inside out. You plug in your limits of integration for whatever variable you integrated with respect to first, and then deal with the outside integral from there. Okay, so here's another example, and we've got an integral that goes from 0 to pi over 3 and 0 to cosine y, and we've got x sine y dx dy. So when you solve this one out, again, the same process here. We're integrating with respect to x first this time. So I'm still going to have an integral going from 0 to pi over 3 of the result of whatever we get here. Antiderivative of x sine y will be x squared sine y over 2. And that's going to be integrated from x equals 0 to cosine y. Okay, and now we need to plug in our limits of integration, and then we're going to integrate with respect to y. So when I do that here, I'm going to end up with, let's see, when I plug in cosine y in for x, I'm going to get cosine squared y sine y over 2. So 1/2 cosine squared y sine y. When I plug 0 in for for x, I'm going to end up with 0. So really, I just have that now dy. Okay, at this point, you can see that we would do a substitution. Your u would be cosine, your du would be negative sine y dy. And in the end here, we're going to end up with 7 over 48. Now, typically, When we work these integrals out by hand, I'm going to allow you to just use a calculator once you get to your single integral, but you'll have to do that outside integral first because your calculator is not going to have the ability to solve a double integral. So our primary focus here for the rest of the time is not really going to be on the actual mechanics of solving the double integrals because I think you can do that part of it. What I'm going to focus on for the rest of this is just going to be the setup of the actual integrals based on the problems and the descriptions that were given. Okay, so when we talk about double integrals over general regions, what we're talking about is an example like this. You can see we've got a rectangular region, the region R here that we've got in this rectangle in this diagram. And now we've got some shape within that region, and we're calling it the region D. So D is within the region R. And notice our function is defined as being f of x if we're in that irregularly shaped region D, and it's 0 if we're outside of that region. So really, when we look at an integral of this function on the region R, we're really just looking at the integral on the region D. Okay, so you can see that those are essentially the same in this particular case. Now, when I go through this next part, I'm going to talk about two cases here, but the reality is you don't really have to remember these as two cases. What you just have to remember is, what integral or what variable are you going to integrate with respect to first. So the first one is going to be what we call a type 1 plane region. So if we have that irregularly shaped region D, and it lies between the graphs of two continuous functions of x, then this is the way that we're going to set this up. So essentially what we're going to do is we're going to integrate with respect to y first, and then we'll integrate with respect to x after that. And I'll explain why when we solve one of these questions here in just a second. But you can see for my domain, I have my x bounded by some constant values a and b, and I have my y bounded by two functions of x. So when you look at the setup, you'll be able to tell after you've done a couple of these which situation you have, and that'll help you decide how you're going to set up your integral. So you don't have to necessarily memorize a type 1 or a type 2 or a case 1 or a case 2. All you really have to do is kind of understand what you're looking at. So keep that in mind when we look at this next part. Okay, so you can see on these three graphs, we've got the same thing where we have our x values are bounded between a and b, and our y values are bounded between two functions of x. So when we're in that situation, this is how we're typically going to set up our integral. And you can see that this is really the part that I'm interested in. I am going to integrate that function with respect to y first. And notice that g1 and g2 are functions of x. So what that's going to do is, after I've integrated with respect to y and substituted in, I'm going to have all x terms left. And then I can just solve that single integral in terms of x. Okay, so that's essentially what's going to happen on these. Okay, so this is kind of telling you how to find the limits of integration. And again, I'm not going to go through it this way because you can kind of figure this out, but if you need an actual process to identify or calculate your limits of integration, this is going to walk you through kind of step by step. Okay, so I don't usually try to think of it as a kind of algorithmic process because I feel like each one of these is somewhat of a unique problem. I think if you just learn how to think through it, I think you'll be better off. But like I said, if you really need it, especially on the first few, you can read through those steps. Okay, so here's an example. It says evaluate the double integral on the region R of xy dA over the region R enclosed between y is 1/2 x, y equals square root of x is 2, and x is 4. Now, nice thing here is they already gave you a diagram. Sometimes on these questions, you're going to be given a description and you're not going to be given a diagram. Now, the diagram really is just showing me my region in the xy plane. And that's the important part for me because that's going to help me determine how I'm going to set up my integral. So you can see with this region, we've got, when we talked about a type 1 plane region, we've got that scenario because we have our x's bounded by constants and we have the y values on this region bounded by functions of x. Okay, so if I'm going to set this up, let me show you how we would typically write this out. So our double integral on the region R of xy dA is just going to be equal to, and remember, my inside integral is going to be with respect to y, and I'm going to work this one out just so you can see it. but we're going to go from x over 2, because you can see when I look at this region, the lower y value on that region would be the line x over 2, and the upper value would be the square root of x, and I'm going to go from x is 2 to x is 4. Okay, so we still have the same thing here, x, y, but remember we're integrating with respect to y first, and then with respect to x. Okay, so the reason that was important is because I want to be able to end up with an integral of a single variable after I've done my inside integral. Okay, so when I solve this out, just like on the first two that I showed you here, we're going to take the antiderivative with respect to y. That's going to give me xy squared over 2. That would be evaluated from y equals x over 2 to square root of x. And now we just have an integral with respect to x. But when I do my substitution here, that's really kind of the key to this. I'm going to end up with an integral from 2 to 4. And when I plug in and simplify everything down, I'm going to have x squared over 2 minus x cubed over 8. And now I've just got a single integral in terms of a single variable. And it turns out for this one, we get 11 over 6. Okay, so that's kind of the main idea behind it. Now, I'm typically not going to actually work through the rest of these as we go through the rest of the practice problems here, because what I really want you to be focused on is the setup at this point. I think the mechanics of solving the double integral are pretty straightforward. So we'll try to really talk through the setups on these. So the second type that you're going to see when we're talking about these plane regions, it's going to be when you have the y's bounded by a constant, and then you can see the x's are bounded by equations that are functions of y. So you have x as a function of y on your left boundary and your right boundary. Okay, so when we set this up, it's just kind of the reverse of the last one. We're going to integrate with respect to x first, because that will give us an integral in terms of y, and then we'll integrate with respect to y second. Okay, so still the same idea, it's just that we've reversed the order here. Okay, again, with the limits of integration, I think if you kind of look at these problems, it makes sense, but you can always go through and kind of read through this if you really need that. Okay, so here is a triangular region, and we want to evaluate this double integral over this region. So it's between the lines negative x plus 1, and y is equal to 3, and we're trying to get the double integral of 2x minus y squared. So essentially, if you kind of want to visualize what is this even representing, we would be finding the volume between this function. You know, you could kind of think it as z is 2x minus y squared, between that function and the xy plane bounded by that region. Okay, so when I set this up, let's talk about how we would set up this integral. So I'm going to solve this double integral on the region R. It's 2x minus y squared. And again, dA, and now we're going to break that dA into the differential pieces of it. So I want to integrate. Notice that I have here my y bounded down here by 1 and up here by 3. So I know my y is going to be the outside integral. I'm going to go from 1 to 3 based on the fact that it has constant values as the boundaries for the y's. Okay, so now I'm going to go on the inside integral in the x direction. It's going to go from, and I have to kind of look at my graph from a rotated view. So I'm looking at it from the highest x value to the lowest x value. So if you look at the graph kind of sideways, you can see that the highest x value is when I'm furthest to the right on that graph. And that would be when I'm at y is equal to x plus 1. Now remember, we're going to integrate with respect to x first. So I want to be left with functions of y. So x is a function of y would be y minus 1. That would be my upper limit. And then my lower is the negative x plus 1. But again, I want x as a function of y. So that would be 1 minus y. And again, I'm still integrating the 2x minus y squared. But remember, we're going to do dx and then dy. Okay, so at this point, it's kind of the same process, right? We're going to take our antiderivative, we're going to plug in for the x, we're going to simplify down, and then we'll have an integral in terms of a single variable. I'll just show you one intermediate step here. If we were to take the antiderivative with respect to x and then substitute in, you'll end up with 2y squared minus 2y cubed, which there's a lot of algebra that happens in there. But now I've got an integral that's just in terms of y, and when I solve that out, I get a value of negative 68 over 3. And remember, it's okay to have negative values for these double integrals. We are thinking of them in terms of volume, but that's just telling me that there's more volume below the xy plane than there is above the xy plane on this region. Okay, so let's take a look at another one. So this is more like what a lot of the homework problems are going to look like. So they didn't give me a diagram this time. It says use a double integral to find the volume of the tetrahedron bounded by the coordinate planes and the plane z is equal to 4 minus 4x minus 2y. Okay, so what we have to figure out here is what exactly are we going to use to kind of think about the region that we're looking at. Okay, so the first thing is I know I'm bounded by the coordinate planes. So let's just write this in a kind of general term. So we have our volume. It's going to be over this region R. We're trying to integrate 4 minus 4x minus 2y dA. And what can be helpful here is to actually draw in what your region is on the xy plane. So that's what I'm going to do. I'm going to draw in my xy plane, and now I'm bounded by the coordinate axes. Okay, so the only other part of this I need then is what else am I going to be bounded by? Well, let's think about if we set z equal to 0. So I'll just write that here. Let z equal 0. And what I'm going to end up with is y is equal to 2 minus 2x. So I actually have a triangular region here if I look at that. So 2 minus 2x, we'll just say 2 is about right here. And we're going to go down something like this. Okay, so there's my y is equal to 2 minus 2x. So you can see I'm bounded by the coordinate axes, and I'm bounded by the line y is equal to 2 minus 2x based on the fact that when z is 0, that's where I would, or that's the equation of the line that would be that boundary. Okay, so now we just have to decide what are we going to integrate with respect to first. Okay, so now notice with the x values. So first of all, when y is 0, we're going to get x is equal to 1. So this would be the 0.10, this would be 0.2. But notice with the setup here, I could kind of do this in either way. It's really a matter of preference. I already have y in terms of x, so that's how I'm going to choose to integrate this. But if I really wanted to, I could get x in terms of y. It wouldn't really make a difference. So what I'm going to do is I'm going to set up my volume here, and I'm going to think, okay, I know that I'm going to use x as my outside integral. So I'm going to go from 0 to 1. On the inside integral, my y's are bounded by 0 and 2 minus 2x. And then from there, the rest of this is the same, 4 minus 4x minus 2y. And then I just have to remember, what am I integrating with respect to first? I'm integrating with respect to y and then with respect to x. Okay, so that would be my setup. Now, like I said, keep in mind, we could have done this where, we said x is equal to 2 minus y over 2. And then we could have set this up and integrated with respect to x and then with respect to y and had y bounded from 0 to 2. It wouldn't really make a difference. So when you have these triangular regions, a lot of times you have options. For this one, if you want to solve it out, you would integrate with respect to y first. And I'll just show you one intermediate step again. What that would give me is 4 minus 8x plus 4x squared. And then I'm integrating with respect to x at that point, and that would end up giving me 4/3. Okay, so notice it's a little more difficult when we have to start thinking about, what is this region actually going to look like in the xy plane. So when you come across problems like this, you don't necessarily need to graph the function itself, the z equals 4 minus 4x minus 2y, but it is a good idea to graph the xy plane so that you can see that region in the xy plane. It'll help you set up your limits of integration. Okay, so here's another example. This time we were given a diagram. And from the diagram, I'm going to use that to kind of determine what I'm going to use for my setup. Now, notice on this diagram, we are going to be finding the volume of the solid bounded by this cylinder, x squared plus y squared equals 4, and the planes y plus z equals 4 and z equals 0. Okay, so nice thing is we have a diagram here. If we didn't have a diagram here, this would be a good candidate for graphing on GeoGebra 3D, because you really want to have a good feel for what is actually happening here. We need to know what our upper function is, what we're bounding everything by. So you've got to be able to kind of visualize what everything is. If you remember earlier in the year, we did a lot of stuff where we were graphing these 3D figures, and it was for situations like this. We wanted to be able to know what these would look like without necessarily having to graph them. But if you need to graph it, go ahead and do that. Now, notice our region in the XY plane's already been determined for us. And the nice thing here is, with the way they've set this up, it makes it pretty clear that we're going to want to integrate with respect to y first and then with respect to x. And the reason I say that is because see how they gave us y in terms of x as the upper and lower boundaries? Well, that tells me if I integrate with respect to y first, I'm going to have just one integral and single integral with respect to x, or integrating with respect to x, and then I'll just have constant limits of integration of -2 and 2. So we could have done that the other way, right? We could have gotten x is equal to the square root of 4 minus y squared as the right side of the circle, and x equals negative square root of 4 minus y squared as the left side, and we could have set it up that way. But since they gave us this information, I'm going to use it in the easiest way that I can. Okay, so what I want to do here to find this volume, remember I said I'm going to integrate with respect to y first, so I know my x is my outside integral, but my lower limit of integration is the bottom of the circle, negative square root of 4 minus x squared. Upper limit is the top of that circle, square root of 4 minus x squared. And then I've got my function. So remember the plane was y plus z is equal to 4. So that's the same as z is equal to 4 minus y. And we're going to integrate with respect to y and then with respect to x. Okay, so when we solve this out, again, fairly simple. I'm not going to work through the whole thing, but I'll show you just a couple of key steps here. Once we've integrated with respect to y and plugged everything in, we're going to be left with a single integral where we've got 8 times the square root of 4 minus x squared dx. Now, sometimes on these, you're going to be asked to give an exact solution. When you get to a single integral, could you go through and plug it into the calculator? I mean, sure, you could. But if I ask you for an exact solution, you may need to solve an integral like this out. And to solve this one, you would actually have to use trig substitution. And some of these integration techniques we haven't used a lot in the last few months. So I've tried to hit you with some of these from time to time, but you might be a little bit rusty on something like trig substitution. We'll talk a little bit about trig substitution in class so that when you come across problems like this, you can remember how to work those types of problems. So that'll be something that we hit on the side because I don't want to get lost in trig substitution right now. When you do solve this entire integral out, you end up with that volume being exactly equal to 16 pi. So in this case, if you had plugged that into the calculator and gotten a decimal, you could divide by pi and you could see that you got roughly 16 and you would be able to see the exact solution. But that's not always going to be the case. You're not always, sometimes you might have something like, 117 over 4 pi, and that's not very easy to identify. Okay, so one other thing we need to look at is sometimes we're given an integral and we want to reverse the limits of integration. So we want to reverse the order that we're going to integrate in. And the reason we would do that is because it might make an integral that we can't solve using antiderivatives. It might, when we rewrite it, turn it into an integral that we can solve using antiderivatives. Okay, so here's an example. We have this integral from 0 to 2 and y over 2 to 1, and it's e to the x squared dx dy. So you can see the inside integral right now, the way it's written. We're supposed to integrate with respect to x first. I don't have any way that I can integrate that with respect to x. but there is an easy way I can modify this. And if I could integrate with respect to y first, well, the antiderivative of e to the x squared would just be y e to the x squared, right? And that would be super easy to do. So that's what I would like to do, is reverse the limits of integration. Okay, so here's my setup. And I want to think of this rather than, having my double integral already written out with my limits of integration. Let's go back to the general setup. Now, if we were to think about what does this actually look like, right? That region is x equals y over 2 to 1 and 0 to 2 on the y's. So let's think about what that would look like. So we've got x equal y over 2. That's the same as y is equal to 2x. Okay, so we've got our x bounded by that line, and it's also x is 1, and then we have y from 0 to 2. So let's just sketch what that region looks like. All right, so let's graph this region just so we can get a feel for what it is that we're looking at here. Okay, so I've got the line y equals 2x. We established that, and we said that we're going from y equals 2x, or x equals y over 2, out to x is equal to 1. So here's x is 1, and we'll say y is 2 is somewhere up here. And so the region that I'm looking at is actually going to be this region over here. Okay, so that is the region that I'm trying to integrate over. Well, now that I've identified that, it's pretty easy to see that I could also flip the limits of integration around and make this to be an integral where I'm going to integrate with respect to y and then with respect to x. And if I do my y first, well, my upper bound is 2x, my lower bound is 0, and then x is just bounded between 0 and 1. And you can see that's what's been done right here. So we switch those around, and now when I solve this integral out, just like I said before, the antiderivative is now e to the x squared y, and I can solve this whole thing out and I can get the solution of e minus 1. So you've got to think about that sometimes. Whenever you get stuck and you can't really understand what to do with switching your limits of integration, always draw the xy plane and draw what that region is based on those limits of integration, and it makes it pretty easy to see how you can reverse the order for your limits of integration. All right, so last thing I have for you here is just a couple of properties that you might see from time to time when we're dealing with these double integrals. And these are the same properties that we saw back when we were dealing with single integrals, back in MVC calculus, or calculus of a single variable, functions of a single variable, I should say. So here we've got a double integral over the region D. Let's say that region D can be broken into two subregions, D1 and D2. And you can see we can just break this apart into two integrals, as long as D1 plus D2 gives you the original entire region of D that you were looking at. If I'm going to integrate a constant function of 1, you can see that the region D multiplied by 1 is just going to give me the region D. So the area of D will end up being the volume of that particular figure. All right, and then the last one, this is actually a really useful property. And we saw this one back in two-dimensional calculus, but we didn't really use it very often. And it's kind of the same thing here. We don't always use this, but it's a nice tool when we need it. And what it is it's a way for me to bound the integral of a function, in this case, the double integral of a function, when I can't actually solve the integral out. If I know the maximum value for my function on the region, and I know the minimum value for my function on the region, then I know that the volume of my integral has to be less than that maximum value times the area of the region, because that would give me a volume calculation. And it has to be greater than the minimum value times the area of that region, because that would give me, another volume that would be obviously lower than the actual value, because I'm assuming minimum value for the entire interval, which is typically not going to be the case. So now we've got an upper bound and a lower bound. So here's an example of one. It says use property 11 to estimate the integral, double integral over the region D, e to the sine x cosine y dA, where D is the disk with center at the origin and a radius of 2. Well, that's not an integral that we're going to be able to solve. So before I start trying to solve this thing out, let's see if we can bound this function. E to the sine x cosine y. Well, the largest that could possibly be, if you plug in x is 0, anywhere where x is 0, we're going to have e to the 0 power. Anywhere that I can get e to the 0 power would be 1. Anywhere that I can get a 1 as my exponent would probably be my best case scenario, right? Because that would give me a value of e to the first power. So is it possible for sine x times cosine y to be equal to 1? And the answer would be, yeah, it could turn out that way. And if it turns out that way, we get e to the first power as our maximum. Now, the minimum value would be if the product of sine x and cosine y would be -1. And you can just think of it this way if you want to think about how do you find that max or the min. Well, the biggest sine can be is 1. The biggest cosine can be is 1. If they were both 1, I get e to the first power. The smallest this could be, sine x, is -1. The smallest this could be is -1. Well, if they're both -1, I'm going to get 1 again. But if one of them is +1 and one of them is -1, that's going to give me e to the negative first power. So now I've got essentially my maximum value and my minimum value. And now what we do is just say, okay, if we want to bound this integral, let's assume that we have the maximum value over the entire region, or we have the minimum value over the entire region. So the only thing we really need here is, what's the area of this disk, of this region D, right? Well, the area of that disk, if it's a disk with center at the origin and radius of 2, it's just a circle. A circle with radius 2 is going to have an area of pi r squared, which is just going to be 4 pi. Okay, so this double integral then can be bounded. So I've got the region D, I'm integrating e to the sine x cosine y, and I've got my dA here. So that has to be less than or equal to the maximum value times that area. Well, that would just give me 4 pi e, and it has to be greater than or equal to the minimum value times the area of that region, which would be 4 pi e to the -1 or 4 pi over e. Okay, so again, it didn't let me solve the integral, but I at least have a general idea for the size. Like, what should the size of this integral be? It should be somewhere between those two numbers. And that's the usefulness of that property is, you know, even when you can't solve it out, at least you have a general idea of the magnitude of the solution. Okay, so as you work through your homework, try to practice with your integration techniques. You might be tempted as you work through these to go through and, you know, do what I did here. You would work obviously the inside integral, and then when you get to the outside integral, you might be tempted to just plug it into the calculator every time. But as much as you can, try to practice that outside integral as well, so that you're practicing with some of those integration techniques. There's going to be times I'm going to let you use a calculator and solve those out. There's going to be times I'm going to require you to solve them and get an exact solution. So if you're practicing with, you know, your integration by parts, your partial fractions, your trig substitution, if you're practicing with all those things, then when you have to use them, it won't be such a struggle. If you've been plugging it into the calculator every single time, then you're going to be having a really, really hard time getting those exact solutions when needed.